Okay, so let's start our current space criteria today. Not current space criteria, but deck transformation criteria. So I have introduced the definition of deck transformation last time, so I won't write it down again. Okay, so you can check my last video. So. Okay. Okay, let's start with the theorem first. Okay, so this is actually term point name. So now that gamma from this x tilde to this x is a universal covering of a connected locally path connected topological space X okay, so and then let x naught unit x and then we let this f to be defined as the gamma inverse of x naught, like the fibers, and then that x naught tilde be well with f be element of this f. Okay. Then we have the following. We then have the following. Okay, so A so the map deck of this gamma to this f given by phi to phi of x not tilde is a bijection. Okay, so yeah, so that's proof formula one. So actually, it has a Yeah. Okay. Let's prove. Sorry. Let's prove let's prove one by one. Sorry. Let's prove one by one. Okay. Okay. So here this is the proof. Proof of part A. Um. Okay. So by uniqueness of universal coverings up to equivalence. Okay. Yes, it's a lemma. For each point, uh, y in this f, there is a unique homeomorphism phi from this x tilde to this x tilde such that okay, such that this gamma composed with phi is equal to gamma, and you have this phi of x naught is x naught tilde is equal to y. Okay, that is the map let's start a new line. The map deck of gamma to f is bijective. Okay, so thus A is proof. Okay. Okay, so okay, so now let's see why let's go through this argument. Okay, so okay, by the uniqueness of universal coverings up to equivalence. Okay. Sorry. And by uniqueness of universal coverings up to equivalence. For each point y in f, there is a unique. Oh, okay. So let me think. So okay. So you know that. So we know that for any universal covering, right? It is unique up to equilibration, where the equilibration is like yeah. I remember we have we have the equilibration lemma, right? No. What do you have? So yeah, so we have that Okay, sorry. Let me think. Actually, yeah. I forgot. Yeah. Yeah. Let me check the lemma. Okay. Uh. Yeah. Sorry. Okay. So. Okay, so yeah, so this X is a connected, locally path connected topological space. Okay, and yes, so the lemma 10.3.2. Yeah, so this is like so this is lemma. Yeah, this is a play that yeah. So there's a lemma that we showed about the uniqueness of universal coordinates, saying that a connected locally path connected topological space has at most one universal coordinate space up to equivalence of coordinate. Okay. Yeah, up to equivalence of coordinates. Okay, up to equivalence of coordinates. So that means that, so let me revise myself. So so if two coordinate space, yeah, so if two coordinate space are, yeah, so if two coordinate space are of the same, yeah, if two coordinate space of the same base space are equivalent, if there is a homeomorphism from this, from the, between the coordinate space, between the coordinates, that is lifting of, so let gamma be the first coordinate, and yeah, so that is a lifting of gamma. Okay. Yeah. So okay. Yeah. So this is the theorem behind this argument. So yeah. Okay. So here, um, wait, for each point. Oh, okay. Why for each point there's a unique? Okay. Let's see here. Well, what do we have here? So. Okay, we know that this X is like locally path connected, right? And then gamma is a universal coordinate space. Wait, what is that? Gamma, okay. Let me think. Okay. Okay, so I think maybe I should state the definition, but yeah, okay, let's see. Okay, so the deck transformation of a coordinate space, gamma from x hat to x is a homeomorphism phi from x hat to x hat, such that this, okay, gamma from console phi is equal to gamma, okay. So, okay, um, okay, so let's see, but you think so each point y in f, okay. So I want, so okay, so for each point y in f, so this, okay, so here you have this x, and then you have this x tilde here, and then this is like a gamma, right? And then you have the base point, let's say x naught, like somewhere here, and then you have this like f, and then you pick one element, let's say x naught tilde, okay? And then let's see what you're gonna do. So oops, sorry. And then yeah, so then okay, so this is a universal covering. Okay, so wait, what is the level that we're using here? So for each point y in f, there is a unique homeomorphism phi from x hat to x hat. Oh, okay, I see. Ah. Okay, so here this is gamma, right? Yeah, so remember this diagram? Yeah, yeah. Okay, so yeah, so what I do is that shoot. Okay, so wait, what is okay. Okay, okay. So here, these stacks, this app is like the stacks, or like the, yeah, it's like the stacks. And then for the same current space, okay, you do the same, you do the same thing, okay, you do the same thing. So here, it's like the app. And then what you do is that you pick, sorry, what do you pick? You pick, let me think. Oh, shoot, I think you should pick the x naught here, right? Because you want the, yeah, you want the y to be here, okay. So let's say that you pick this is y, and then let's say this point is like your x naught tilde, okay. So there is a unique homomorphism phi from x hat to x hat, okay. I think once you, because these gammas are universal coverings, so I think once you specify the start, yeah, once you set it, yeah, once you set what do you do? Yeah, I want to say that once you specify like the fixed point, then wait. Let me think. Okay. Okay. Sorry. let me check. So. let me think. Okay, I think it's corollary 10.2.6, right? Yes. Okay. So this is corollary 10.2.6. So basically, this X is locally path connected. Sorry. Yeah. Connected, locally path connected, and then this X tilde and X. This X tilde and X tilde, they are also connected, right? Because it's still connected, and then this path connected. So therefore, it is connected. Okay. And then then we have that this pi one is like contained in the pi one. Sorry. Yeah, because it's still connected. Therefore, yeah, you have the pi one containment, right? You have the pi one containment. Okay, and then what you have is that you will have you will get a lifting. Okay, so there is a unique lifting such that so once you fix the starting point x naught and like the landing point. Yeah, so basically if you fix a base point use this x and then to pre-image point one in x tilde and one in x tilde, then there is guaranteed a unique lift. Okay. Okay. Yeah. So then, but then if they're equal, then I think by the same lemma, it's a homomorphism, right? So yeah, so we get a unique homomorphism here, and then so that is okay. Yeah. Okay, and then so x tilde equal to y. Yes. Oh, okay. Yeah, it's true. Okay, it's true. Because if you say it's bijective because this y is arbitrary y, right? So and then but it's a unique map, right? So basically, if two so if two algorithm maps x naught to the same image, then it must be the same thing, right? Because because of uniqueness. And then okay. Okay, and then so so it's onto, and then it is injecting. Okay. Okay. I think that shows the I think that shows the result. Okay, I think that shows the result. Okay. All right. So okay. So let's see what's the next one. So Okay, so let's take part B. Okay. Okay. So for part B, so part B says the map. The map chi from deck of gamma to f. Oh, sorry, to pi 1 of x naught given by phi to this okay, gamma alpha tilde with base point x naught. Okay. Where alpha tilde is an arbitrary path in x tilde from x naught to phi of x naught. Is x tilde from x naught tilde, okay, x naught tilde to phi of x naught tilde. It's a well-defined group isomorphism. A well-defined group isomorphism. Okay, so yeah, so group isomorphism means that you have this it's a projection, right? And also it's a I think it's a projective homomorphism, right? This is group isomorphism. Okay, so okay, let me check. What is group isomorphism? Okay. Okay, I'll leave it to you to verify what is isomorphism because yeah, I couldn't find the yeah. So I think it's just like you have a group homomorphism, and then it's also injective. It's also a bijection. Okay, so that gives you isomorphism. Okay, so now what happened is okay, so now the map okay, so now the map deck gamma to pi 1 x naught given by phi to this gamma of alpha tilde in this x naught, a center at x naught, where its gamma tilde is an arbitrary path in x tilde from x naught to phi of x naught, from x naught tilde to phi of x naught tilde is a well-defined group isomorphism. Okay. So yeah, I think what I said is okay. Maybe let's do it again. Okay. So here, what is the map? So the map is that you take any element from the deck transformation, right? Okay, so basically what you do is that you take any phi and then you map it to where, oh, okay. It's an arbitrary path, the x tilde from x naught to, oh, okay, from x naught to phi of x naught, okay. It is a well-defined group isomorphism. I see. Okay, let's do the proof. Okay, let's do the proof. Okay. All right. Okay, so let's do the proof. Okay. So for the proof, we have that. Okay, so suppose that for j equal to 1, 2, phi j belongs to deck gamma. And then yj is equal to phi j of x naught tilde. Okay. Oh, sorry. Yj is equal to phi of phi j of x naught tilde. Okay. And then we have that. And then we have this alpha tilde j from this 0, 1 to this x tilde is a path with initial point alpha tilde j of 0 is equal to x naught tilde, and terminal point alpha tilde j of 1 is equal to yj. Okay, so yeah, so basically what you do here is that you take two elements of the deck transformation, okay? So, and then you define the yj to be the corresponding image of these maps, of x naught under these two maps. And then you define like we define two paths that connects this same initial point, okay, but correspond to these two different terminal points. Okay, so and then what you do is that, okay, so in particular, you have this alpha j, which being defined as the gamma of this alpha tilde j is a loop based at x naught. Base at x naught for j equal to 1, 2. Okay. Okay, so let's see why this is a loop. Oh, wait. Okay, so yeah, so you have so you have this x. Yeah, so let's use this one. Okay, so this map. So here you have this okay, so you have this x naught being, maybe it's better for me to draw here. Okay, so here you have the base point x, and then you have this sorry, what do I have? Oh. Oh, okay. Okay, I see. So, okay, because the initial point is x naught, and the terminal point is yj, right? Okay, and then we know that this yj is what? We know that oh, okay. Yeah, so we know that this yj must be lies in the gamma, lies in f, right? Because gamma of, because this phi j is in the next transformation, so therefore we have the gamma composed with phi j is equal to, wait, equal to gamma, okay, equal to gamma. So, and then therefore, yeah, so therefore you have this gamma of yj is equal to, sorry, yeah, gamma of yj is equal to what? Oh yeah, you have this gamma of yj is equal to, wait, gamma of x naught, right? Sorry, gamma of x naught tilde, and then this x naught tilde is in what? X naught tilde is in f. Okay, so that's what I think is the proof. So okay, so then okay, so yeah, okay, so okay, so yeah, okay, so wait, gamma j, what is, okay, yeah, so yeah, so since you have since you have the map that you have the phi over this yeah, I think that gives the proof, right? Because so namely because the gamma of yj is always x naught, right? No matter, yeah. and then you have that yeah, and then okay. Anyway, so let me just continue here. Wait, okay. Okay, let me see. Let's see what happened next. It's a loop with an external for okay, yeah. So if y is equal to y2. Okay, so if y is equal to y2, i.e. Phi 1 is equal to phi 2. Okay, then then since this x tilde is simply connected, okay, this we have that. Okay, this alpha 1 and alpha tilde 1 and alpha tilde 2, and therefore this alpha 1 and alpha 2 are path-homotonic. Okay. Okay, so let's see why they're path-homotonic. Okay, so we know that this x tilde is simply connected, right? So yeah, this is by definition. Okay, and then wait, why you have this y equal to y2? Yeah. Okay. This is. Oh, okay, okay. Yeah. So you just have the okay. Yeah. Okay. Let me see. So. Okay. So here you have that. Because this alpha tilde, right? So these alpha tilde j's, they are like loops on the covering space, right? And then, wait, yeah, and then yeah. So what happened is that, what happened is that, let me see. Yeah. So yeah. So basically, if you pick the point, y1 is, yeah. So if you do the same endpoint, because they all start at the same point, right? So therefore, at the same turning point, so it's just like you have the map. Let's say this is like x naught tilde, and then you have this yeah. So you have the x naught tilde here, and then maybe you have another point let's say y1 equal to y2, let's say y1, okay, which is same thing as y2. Then you have like these two paths here, and then oh shoot, they are not moving as well. Okay, and then so they form a they form a loop, right? So yeah, so they form a loop therefore, and then basically since this, so yeah, you will have this so since they form a loop, you will have this one okay. Okay. Yeah, so since they form a loop, therefore, oh, what do you think? Yeah, I think you can do some argument in the using like using a homotopy to show this, but yeah, let me think. Yeah, alpha one, alpha two. Yeah, so this is like alpha one, and then you know that this is like alpha two, that. So you know that this alpha one follows alpha two negation is homotopic to, yeah, is homotopic to the constant loop at base point, right? Yes. Okay, so this you know, and then what do you do? So okay, so yeah, sorry, I forgot. So I think you can do that. Okay, I think you will be able to show that. You using the fact that it's like simply connected. Okay. Okay. Yeah. Yeah. Sorry, it's not. Yeah, it's not on top of handout. So okay. So okay. So let's just continue. So. Yeah, so I believe that this, I believe that this alpha 1 and this alpha 2, they are homotopic. Okay. Sorry, alpha 2 or alpha 1 2 alpha 2 are homotopic. And then, so therefore, you have this alpha 1 and alpha 2 are path homotopic. Okay, so why is alpha 1 and alpha 2 are path homotopic? Oh, okay. So because yeah, you have a homotopy upstairs, right? So then you do a projection. That's also a homotopy, right? Because uh, you have paths upstairs, then you do a projection. It's a path. It's a okay. You take the